Hi, I'm Baptiste Genest. I'm a French PhD student, and today I'm going to talk to you about BSP-OT sparse transport plans between discrete measures in loglinear time. And this is a joint work with Nicolas Bonneel, Vincent Nivoliers, and David Coeurjolly. So, as the title suggests, I'm going to talk to you about optimal transport. So, what is optimal transport? Well, in its simplest form, it is the following problem. I give you two sets of points, x and y, and they both have the same number of points. Okay. And I want you to find an assignment between x and y, so a one-to-one mapping, such that the effort that you would have to make to move all the particles of x from where they are to where they should be as small as possible. Okay, and we typically define this notion of effort as a sum of a transport cost. And typically, this transport cost is going to be a power of a distance. Okay, so here, for example, I illustrate everything with the simple Euclidean distance. And so in this case, it's this assignment that is the optimal one. And so if you look at this figure long enough, and if you think about this problem long enough, you might convince yourself that this is actually a very meaningful problem. It defines a meaningful notion of distance between those two point sets. If it's very cheap to move optimally all the particles from x to y, that means that in some sense they are quite close, and vice versa, right? And so that's exactly why this is very good intuition, because that's exactly why optimal transport is so useful in so many areas of mathematics. Okay, it is a very beautiful theory that is very useful in probability, in PDEs, etc. And it's also very useful in machine learning because it allows you to compare, to define this notion of distance between probability distributions. And so it has many different formulations, but here we only focus on the discrete to discrete case. Okay, so essentially weighted point clouds towards another weighted point cloud. Okay. And what we are interested in today is that it has found many nice computer graphics applications. Okay. Uh, so that sounds very, very fun, very nice, but how hard is it to solve this problem? Well, um, the thing is, if you attack it naively, you're very quickly going to realize that there are simply too many bijections. Okay, because there are actually as many bijections as there are permutations. Okay, and this means that you basically cannot use a brute force approach because you have simply n factorial number of permutations, and so that's completely intractable. And so the thing that's hard here is that it is phrased as a combinatorial problem, right? Which are in essence very hard. And so, historically, everything became much simpler when people started to consider the convex whole of the set of assignments. Okay, and so now it is not an assignment; it is a transport plan. And what changes is that now everything is continuous in the sense that no mass can split. Okay, a point in X can say I'm going to send 50% of my mass to this one and 50% of my mass to this other point. All right. And so essentially it changes a lot of stuff, okay? And the main thing is that you can now rephrase everything as a linear programming problem, okay? Because now you simply optimize for a linear cost function over a convex set. And so you can simply use the linear programming tools and you can obtain an exact solution using, for example, the simplex algorithm with an n-cube complexity. So it is, of course, still not scalable at all, but much more attainable than n factorial. And it's, in practice, like much simpler to study in theory and in practice this problem when you phrase it as a linear programming problem. But all of this is very important to understand our contribution, okay? Because our method is essentially like focused on sticking to this combinatorial problem. Okay, and because like the state of the art for scalable OT will either give you a flow to move the particles from X to Y, okay, or simply an approximate transport plan that would rely on this linear programming approach, and so that won't be this transport plan won't be optimal in general, but that's okay. But just it's in general just won't be a bijection between 2 point clouds. Okay, and so that's our contribution. We are the first method that is really, really efficient and scalable, that is able to produce high quality assignments between point clouds. Okay, so how do we do that? Well, our pipeline is very simple. Right, first, in a first step, we can generate k random bijections in parallel that are all of decent quality for the optimal assignment problem. Okay, they are not optimal, but they are quite good. Okay, and then in a second step, we simply merge bijections one by one in order to reduce the transport cost step by step. Okay, such that in the end, we always remain bijective and we end up with a bijection that has a very low transport cost. Right, so how do we do that? First, how do we generate those random bijections of decent quality, and that works in any dimension? So we are going to start from the basics. Okay, optimal transport is trivial in one dimension. Okay, and so many techniques will rely onto this fact and will first project the points onto a 1D line. And then you can solve the optimal transport problem there. Because the optimal transport problem along the line is very simple. You just have to sort the points. Okay, and once they are sorted, you can simply assign the first point in X to the first point in Y, and then in second point in X to the second point in Y, etc., etc. And this gives you an assignment that is optimal along this line. But when you pull back this assignment to the original point, you see that essentially it is like quite bad because we lost too many information during the projection step, and so we end up with an assignment that is a very low quality along this single slice. Okay, and so this was the original idea. Could we keep this algorithmic simplicity while retaining as much as possible information during the process in order to end up with a bijection that is of much higher quality, right? So how do we do that? Well, we are going to use a very simple recursive approach. Okay, you pick your 2 point sets and you pick a random direction. Okay, that has to be the same for both point sets. And then you can simply use this direction to split your point sets in 2. Okay, and make 2 groups in X, 2 groups in Y. And what is important is that each corresponding groups that are of the same sign from the split must have the same number of points, right? And then I can repeat this process recursively by choosing another random direction, splitting my point sets in 2, and starting again recursively. And what is really important is that they always have the same number of points on both sides, such that they always end up with a trivial case when I have 1 point in X and 1 point in Y. Okay, such that I can simply match those 2 points together. And so that is only one execution of this recursive process. But if you do all the branches of this recursive tree, you end up with this, an assignment that is of much higher quality than a one that has been built from a single slice, because we used much more projection during this process. All right? And so if you think about it, it is actually equivalent to building 2 BSP trees, binary space partitioning trees, at the same time on both of your point sets and matching the corresponding leaves. All right? And so it is actually quite elegant because it also generalizes the quicksort algorithm, etc., etc. And so we end up with a n log n complexity just as for the optimal 1D case. And so it turns out that this procedure had already been studied in this bijective setting, okay, using axis-aligned splitting directions. And a part of our contribution is to extend the BSP matchings to other settings of optimal transport. Okay, for example, the partial transport case, where you have more points in Y than in X. And so not all the points of Y are going to receive mass. And also in the non-uniform case, where each point can have a different mass. And I don't have the time to dive into the details, but essentially what you need to be careful about in order to generalize BSP matchings to these settings is how do you split your point sets in 2 at each step of the recursion. Okay, and if you do that carefully, you can ensure that you always satisfy the mass assignment constraints, and so that's what makes it work. Okay. And another contribution that is very important in practice is how do you pick the slicing directions? Okay, that must be random. So we start from the fact that the optimal map between 2 Gaussians is known. Okay, we know that it is given by a simple affine map. Okay, and we show that if you choose any eigenvector of this affine map, you define directions that will naturally split the transport in this Gaussian case. Okay, and so at each step of the recursion, we just have to approximate our 2-point clouds with Gaussians. We compute this transport matrix, and we pick at random any of its eigenvectors. Okay, and we show that it drastically improves the quality of the final BSP matchings, much more than a single than random slicing or using orthogonal slicing. Okay, so really Gaussian slicing is very impactful in terms of quality. And so that's really nice, and this allows us to go from a single slice which is very low transport quality to this one with a single BSP. Okay, and so as you see, it is quite nice already, but it's clearly not enough, right? Because BSP matching will clearly show linear separation artifacts, right? Because you can clearly see where the points has been split into. All right, And so we really need this second step that is about merging two bijections together to reduce the transport cost, and that will drastically improve the quality of the bijection. So to do that, we have two ways. Of doing so. Okay, the first one is very local. So you have a current bijection T that maps x1 with y1 and x2 to y2. Right? And I have a new bijection T prime that comes in and that proposes to assign x1 to y2. And I just want to check, can I improve my current bijection by following this proposal? And so if I want to remain bijective, I need it. I want to give it a try. And if I want to remain bijective, I also need to assign now x2 to y1. Another thing that is very important here is that this assignment from x2 to y1 might not have been proposed by neither t or t prime. Okay, so that's really what helps with breaking linear separation artifacts. Okay, but so this gives me a new local configuration. Okay, so x1 to y2 and x2 to y1. And I can simply check, is this new configuration better than the old one? And if it's the case, I can simply keep this assignment. Okay, and then I simply do that for all the points in X. And so that already works quite well, but it is very local. And so we have another way that is purely global. So you consider at the same time the union of those two assignments of T and T prime at the same time as a graph. Okay, and then onto this union graph, you can compute the connected components of this graph, and this gives you a decomposition of this union of assignments. And then per connected component, you can simply keep the better assignment, so the assignment that has the lower cost per connected component. And when you merge everything back together, you end up with an assignment that is of much higher quality than you end up with an assignment that took the best from T and T prime. All right? And so that's it. Very simple. Okay, please keep in mind that everything that we saw is very simple and is very easy to implement. And what is remarkable here really is that these two simple procedures allows us to go from this, so a single BSP, to this, which is visually indistinguishable from the optimal map. Okay, and as you see, everything that we just showed is very simple and some very algorithmically efficient, because as you see, it scales really well. So like, for example, for several hundreds of points here, for example, in 2D, it takes less than 1 second, right, on the CPU. So with very simple code, and it scales well to any dimension in terms of time complexity. Okay, and we show that we reach very good local minima, so typically less than 1% of relative error. All right. And in terms of application, I won't dive into the details, but essentially we are useful everywhere optimal transport is useful. Okay, and so we show in the paper that we can apply it to topological data analysis, image stippling, intrinsic blue noise manifold sampling, and even color transfer, where like a target image can be expressed as a permutations of a style image. Okay, so that's quite nice. But essentially, the key takeaway here is that for like among other methods that use optimal transport, at the same level of quality, we are each time several times faster with simple code on the CPU. Okay, so really that's what's interesting with the method. It's very efficient and it's super simple. Okay, and so essentially we show, like to conclude, we show that BSP matchings are a very efficient way to parameterize and explore the set of relevant sparse couplings for the optimal assignment problem. Okay, and we show that only working with the sparse assignments, so bijections, injective, and other sparse couplings, allow you to use a very simple discrete optimization that will efficiently reduce the transport cost. Okay, and everything is super simple. And so, of course, a limitation is that we only reach local minima, so we have no guarantee on the final result because it is a greedy algorithm. And we even have a failure case that we detail in the paper. And finally, another interesting future work is to extend BSP matchings to other settings of optimal transport, for example, on non-Euclidean geometries, or to the Gromov-Wasserstein problem, and all that kind of stuff. And so that's it. Thank you very much for your attention. And here is a QR code to the source code if you are interested about this project. Thank you.